Very good afternoon to all of you. First of all, let me thank the organizers for giving me this opportunity to present on this totally indigenous technology, that is alkaline water electrolyzers. So unlike Professor Revankar, I will not be talking about the global status. I will be sticking to Indian conditions. Foreign delegates, kindly excuse me. So during the course of presentation, what I would like to carry on is, first I will say why nuclear is required, and second, why hydrogen, and finally I will come to why alkaline water electrolyzer. So all this I will finish before lunch break, of course, well before lunch break. So this is the current installed capacities of various electricity production methods. This is available in the Ministry of Power website. So this is the latest status as on October. So if you, as you can see, the maximum power production is through this fossil fuel, that is the thermal power plants using mostly coal. So almost it accounts for almost 52%. And if you see the installed capacity of renewables, that is solar and wind, that accounts to almost 25%. But if you see the net power connected to the grid, actual utilization in the grid, you will see this coal-powered plants are supplying maximum almost to the 72%, and whereas this solar and wind, they hardly contribute 8%. So that is because intermittent nature of this power sources. Thank God Indians are not praying to the sun god to shine 24/7. So the summary of this slide is, if you want to go for net zero, you should have a base load of fossil fuel based thermal power plant along with carbon capture and utilization and storage, or you go for nuclear. So as per the current technology of CCUS, the energy, the cost is much higher than the nuclear. So this is the, with the current level of technology available for CCUS. Or you have to go for renewable with the energy storage. So if you see the energy supply, so most of the industries use fossil fuels directly as energy source. So here also again you can see almost 50% of this energy is consumed either through coal or oil or the natural gas. So all these generate CO2, and if I can use some of this energy, if I can replace some of these energy sources with the green hydrogen, I will be getting two benefits. That is, I will be addressing this CO2 emissions of the major industries, which Professor Revankar also mentioned. And also, as far as Indian conditions are concerned, I am reducing this foreign bill, which is to the tune of almost $100 billion as of now. So now let us see why hydrogen is required. See, hydrogen is a very versatile energy source. It's a clean fuel, and it's used in many industries as a process gas. So currently, as Professor Revankar also said, we are producing almost to the tune of 5 million metric tons per annum, and most of it is produced through fossil route, and which in turn generates almost 10 times this production of hydrogen, that is the CO2 generation is almost 10 times. So cognizant of these things, Government of India has announced this National Green Hydrogen Mission with an outlay of almost 20,000 crores to be spent in the next 5 years. So the major target is, you can see almost production of 5 million metric tons of green hydrogen. So it involves a capital outlay of almost, investment of almost 8 lakh crores. And if you see this energy requirement for production of green hydrogen. So this requires an electrolyzer. If you go by alkaline water, you need an electrolyzer of the capacity of almost 30 gigawatt. And why I am stressing this, this is mainly important for Indian industries. This is a golden opportunity to exploit this investment of Government of India in this one. So what is the source for hydrogen? So since fossil is ruled out, so water is the only option. And the statement says water will be the coal of future. This is not my statement. This is a statement of Jules Verne, a French novelist, who is also called father of science fiction. He writes in one of the novels, yes, my friends, I believe that water will be one day employed as fuel, that hydrogen and oxygen will will furnish an inexhaustible source of heat and light. Water will be the coal of the future. So, very rightly said. I don't know whether he has given any clue for splitting of water, but what I suggest is go for nuclear. So, let us forget all the colors. Let us say it's a nuclear hydrogen without any color. So, we have all the three options as was told earlier. The best is thermochemical cycle. So, BARC has done its studies both on IS process. It has demonstrated at 150 NLPH, which is the highest in the world. And it has also demonstrated on this copper chlorine cycle, as was told earlier in the discussion. So we have demonstrated it at 5 NLPH. That is a 4-step copper chlorine cycle, which is the first in the world to our knowledge. Because in one of the earlier meetings in IAEA, even these Canadians appreciated this work. So I believe it is the first time in the world. And we have done some baby steps in steam electrolysis. So we have demonstrated this basic technology at 10 NLPH. And both these are under our fast track mode. So BRC is fully working on this one. Whatever you say, at the current technology readiness level is hardly 4 because we have demonstrated it at the bench scale. So it will take some years before it becomes commercial. So to address this green hydrogen, which is required by this our national mission, so we have left with no other technology other than the electrolysis. So this is why we are stressing on this alkaline water electrolysis, which is a proven technology now. So let us focus on this alkaline water electrolyzer in detail. So just fundamentals, for an electrolyzer, you need an electrolyte and the electrodes and of course this DC power supply. Some fundamentals about this electrolysis, because this will be very useful when you interpret this data of these commercial producers. So you have a reversible voltage of 1.23 and of course this thermoneutral voltage is around 1.48. And as you increase this current, there will be ohmic loss in the electrolyte, so which is proportional to this distance between the electrodes and also depends on the resistivity of the electrolyte. So ideally you try to reduce the gap between the electrodes. Of course, there is a chance of mixing of hydrogen and oxygen, so you need to have a diaphragm. So that is the first loss, ohmic loss. And then there will be some over potentials because of the electrodes, and of course there is a small amount of ohmic loss. So the important point is, as I increase my current density, electrolyzer stack size will come down, it becomes very compact, and your capex will come down. Whereas, since the losses are increasing, efficiency will come down slightly, and hence the OPEX will increase. So here is where you have to do the optimization with respect to current density. So let us take this case of electrolyte. So since the conductivity of water is very poor, so we need an electrolyte. So we are going for potassium hydroxide. As you can see from this graph, around 30% gives the best conductivity. And of course, as you increase the temperature, conductivity improves, but effect of corrosion has to be monitored. And selection of these electrodes, of all the options, we have gone for nickel. And also in the nickel, shape of the electrode is very important. So since we need high current densities, we have gone for a porous nickel electrode, which is our customized design, method of fabrication we have developed, which gives a porosity of almost 70%. So which can go of a current density of almost 5,000 amps per meter square. So as I said earlier, we need an membrane. So the older plants, what we have supplied, we have given the asbestos. Since the asbestos is being banned, so we have gone for now indigenous polysulfone-based membranes. So this is also undergoing rigorous testing. So, and ionization membrane is under developmental stage. So this is how we started our journey, somewhere in 2005. So we have started with the 4 NLPH and gradually increased to 1,200, and finally we have gone up to 10,000 NLPH. So the basic scale-up methodology is increase the diameter of this electrode as well as increase the number of cells in the stack. So both these methods were adopted in coming to this final shape. Turn-down ratio, which can be easily coupled to variable renewable energies, and of course on-site, on-demand on-site hydrogen production, because this startup time is hardly a matter of minutes. So otherwise we have this modular scalability, because once I have 10 meter cube or a higher size, further scaling up becomes modular. So this is just a schematic of this overall plant. So we have electrolyzer. So we have this outgoing gases, which is a mixture of KOH with the hydrogen. We have a gas separator. Since there will be some entrapment of alkali, we have an alkali scrubber. So at this point, I can get a 99.9%. And if you want higher efficiency of higher purity of hydrogen, we have this catalytic recombiners. So these are these catalysts what we have developed for this increasing the purity of the hydrogen, mainly palladium based. So different shapes and sizes have been optimized. So this is the total package for our 10 meter cube per hour base technology of alkaline water electrolyzers. So it has got all the utilities. So if you compare with these international electrolyzers, of course, we have just started at 10 meter cube per hour. So whereas others are very well matured and well established. So overall, if you can see, this specific energy consumption is more or less comparable with these international standards. And our pressure is ambient conditions. In fact, our gut feeling is this, if you increase the pressure, even this can improve. So efforts are on in this direction. So many Indian industries have taken this technology, and they are working closely with us, because scaling up is an important aspect. So unless we work with the industries, it is not possible. So this is our roadmap for scaling up of these electrolyzers. So right now we have at this stage, we would like to go in the sequential manner, because scaling up now henceforth will involve increasing the diameter of the electrodes as well as increasing the number of cells in the stack. So both are very challenging ones. So we are working in a holistic manner. So both on the cell stack side as well as the process kit side to improve the efficiency, enhance the durability, safety and reliability, and of course the cost reduction, which is very essential, which we are working with the industry. So we are also working on the electrocatalyst because any reduction in voltage will increase the efficiency and improve the efficiency. And CFD simulation is one of our strong points, which is very essential to optimize this stack design and of course the electrode design. So we are working in this. So this is just to give an idea how these CFD models are very essential. So don't go by these numbers. So it's very important is this, since this, all these cells are connected in parallel, the flow distribution across each cell is very important. So as you increase the number of cells in the stack, the flow distribution is not uniform. So this is a real challenge because if this distribution is very high, our feeling is if it crosses 25%, there can be dry out of the electrodes. So the port design of this stack is very, very essential. So we have also this GUI-based software for optimizing this electrolyzer stack. Since we are bound by this confidentiality, these things I am not disclosing many of these features. It's a very comprehensive software where I can give this size of my electrode, port sizes, and check out this temperature of these gases, pressure drop, and all the parameters which are essential for design. And thereby I can go into this optimization very fast. So as I said, we are closely working with the industries. So the first step is we have gone for 30 meter cube per hour stack. So that is 150 kilowatt. So already we have received a prototype stack of 6 cells. So this is also performing satisfactory as per our design intent. So now the scaling up for this, increasing this to 150 kilowatt is going on with the vendor. So he is our one of our licensees. And the second, parallelly, we are going for the higher scale. We had an MOA with BPCL, or refinery major. So that is for 0.5 megawatt stack. So here also we are in the advanced stage. We have received one prototype 6-cell stack, which is undergoing testing. So far the results are very satisfactory. So far we have operated almost for 200 hours. So without any, all the voltages and parameters are as per our design intent. So we are confident that we will be able to scale it up to full stack based on these observations. So this is an interest for our Indian industries. So this is based on our experience so far with the fabrication of electrolyzers of various sizes. So you can see here, so this major cost, that is the stack cost, will be almost 50% of the total electrolyzer cost. And even then, even within a stack, electrode cost itself is almost 50%. So these are the very two critical factors. And here also we can see this economy of scale. As I increase my scale of electrolyzers, that is, as I go up to megawatt level, the production cost also will come down. So this is the values currently quoted in the market, $1,000 per kilowatt. So we are almost near that. And of course, this will definitely improve once the industries come in a big way. So as I said earlier, this asbestos is being phased out. We have developed our indigenous mixed matrix membrane. It's based on polysulfone polymer. And these are our casting machines. So right now we can make membranes of 500 millimeter width. So since our electrodes are now at least 1 meter diameter and higher, so we need to scale it up these things. So these parameters are almost equivalent to this zircon, which is European standard membrane. performance is almost matching with that. We have high hydrophilicity and a very fine pore size, which is very essential for this membrane materials. So this also we are scaling it up with the collaboration with the industries. So many industries are showing interest because this membrane prices are also going up in the international market. So we need to be self-reliant on this also. So we are confident we will be successful in this. So our roadmap is as follows. So 0.5 megawatt is already under testing. So hopefully by next June we will be able to make a stack, and parallel designs for 1 megawatt is almost ready. So we will be doing this testing of this stack by next end of December, 24 December. And once at least a stack of 0.5 megawatt or 1 megawatt is ready, we would like to test this electrolyzer either by coupling to the nuclear power plant or to the solar. We want to finish it demonstrate by December 25. So these developments have been done with the collaboration of interaction of many divisions in BARC. So this I am mainly telling from the industry partners who are present here. So if you buy our technology, please be assured that there is a good amount of talent in each and every field of this technology who are ready to help you, and you become market competitive. So heavy water division is the main division which is developed this electrolyzer. Chemistry division is working on this catalyst. Desalination membrane technology divisions, they are working on that mixed matrix membrane. So chemical engineering division expertise in this CFD modeling. And glass and advanced material divisions, they are working on these other methods of making these electrodes so that we can reduce this cost of electrode making. So as I said earlier, we are going very strongly on this nuclear power plants. We have established our PHWRs of 700 megawatt. We are going very strong on this one by installing fleet mode reactors. And we have demonstrated nuclear desalination. We are the first in the world. And in the coming years, we would like to be the first by integrating nuclear for producing this hydrogen. So let us try our best.